All right, so today we're going to continue looking at multiple regression for the same exact problem that we were dealing with for the last 2 weeks probably, right? Predicting prices of Toyota Corolla, okay? So what we discussed in the previous class was when I pick my only predictor to be the mileage, that's actually underfitting the model. Remember we discussed overfitting when we talked about classification trees, and overfitting was what? Model is too good, right? It follows the data way too closely so that it picks up the main trend, the main pattern that is hidden in the data, and the noise. But this is the noise which is specific to the training set, right? That's what we basically discussed in overfitting, right? You build too detailed of the model, you get overfitting, okay? Too good. Therefore, it does not generalize too well. You apply the same model to the data set that model never seen before, you get bad performance. Why? Because the noise is different in your new data set compared to what it was in the training set. Therefore, the noise is not predicted very well, right, by the model. But when I claim that mileage is the only thing that matters for pricing of the used car, I was actually underfitting the model, okay? It was too simplistic, right? And how did I know? My R squared wasn't good enough, okay? R squared, do you remember what was R squared for the model with mileage only? 0.35, yeah, 35% of variability in Corolla prices were explained by the mileage variability, right? That's basically not very great accuracy. So my model is too simplistic, right? I'm underfitting the data. And in order to avoid that, here's what we decided to do, right? We decided, hey, let's use all predictors, okay? So let's run this script one more time, just to make sure that we have it all in the memory. So Corolla data and linear regression, I'm using the same function LM, linear model, right? And now I'm using all predictors. And price is my target just like it was before, right? And here's my summary, okay? And what we started doing basically is using this summary, I started to write out the expression for my multiple regression model. The only thing I'm looking at that, and all of my coefficients are not in the right form, right? This is called scientific notations, right? How do I get rid of scientific notations? Do you remember? Options, right? I say options, and then scientific 10 equals just the numbers, right? And if I rerun my summary, this is when my coefficients and p-values as well, by the way, right? They're all in normal, usual notations, not in a scientific format. Okay. And in the previous class, we started to write out the expression for the regression, right? We started with numerical predictors, okay? So price equals, here is my intercept, which comes from the output, the summary of the model, right? Plus age times the coefficient, plus mileage times the coefficient, etc. And the weight was our last coefficient, right? Weight was our last numerical predictor, okay? And then we started to deal with non-numerical, with categorical predictors, right? So this is what we basically ended up doing. We ended up saying if color is metallic, right, then you have to add this coefficient to the model and 0 otherwise, right? Why? Because metallic, the variable metallic, was encoded in my data as 0, 1. 1 if it is metallic and 0 if it's any other color, right? And similar situation was with transmission type, right? We had manual or automatic. The variable was called automatic, okay? And so we added, if automatic equals to 1, that means that car is automatic transmission, so we add plus the slope, which is quoted in my output, 186.22, and otherwise 0, that means you have to add 0 to the model, right? And let's do the last one, right? The last variable that I still have, last predictor is fuel type. okay? And I told you that there are 3 levels for the fuel type, right? 3 different categories. So fuel type, let's go back. So fuel type, all right. Fuel type, we have 3 levels, okay? It can be either CNG, condensed natural gas, or it can be diesel, or it can be just regular gasoline, so gas, okay? So here is how we can encode how we can include the variable fuel type, this variable right here, okay, in our model. So again, the base or reference level is the one that either first numerically or the first alphabetical, right? So CNG, diesel, and gas. Which one comes first alphabetically? CNG, right? So therefore, if the car runs on the compressed, CNG stands for compressed natural gas, I guess, yeah. Then I have to add 0, right, to the model. 0 if fuel type, fuel underscore type equals CNG. So this is my base scenario, right? Just because it comes first alphabetical. There is no other reason, really, okay? Benchmark category, okay? And then if the car runs on diesel, then I have fuel type diesel plus 774.27, this one, right? So here I have to add plus this much if fuel type equals diesel, and also if finally it runs on our good old gasoline, fuel type gas, then I have to add this value, right, plus this much if fuel type equals to regular gasoline, okay? And that's basically my equation, all right? Any questions? How can I write it down? Okay, but note that, and this is the question which is fairly popular on the exam, okay, especially the final exam. Note that even though I have 3 different values for the fuel type, CNG, diesel, and gasoline, I have only 2 variables, and these are weird variables, right? My initial, original variable in my data set was fuel type, right? Column fuel type, and it has CNG or diesel or gas, so all these entries, right? Now on the output, I can see there is fuel type diesel, there is fuel type gas, but there is no fuel type CNG, right? Here is the reason, okay? Remember I told you that if you have a categorical predictor, in the previous class we discussed that, and it has k different levels, k categories, then you need k minus 1 dummy variable. And that's exactly what is happening right here, okay? So if I have my original variable fuel type, 3 different levels, okay? This one is base level, right, or benchmark, right? We add 0, okay, to the equation if the fuel type is CNG, okay? So for each other level, R creates a special dummy variable. So there is dummy variable fuel type diesel, as you saw on the output, right? And there is also another variable fuel type gas. Okay, there is no underscore. Fuel type gas. And here is how you can actually record the same exact equation. Okay, you can. Well, first of all, let me draw a table. Okay, that corresponds to how we determine the coefficient. All right. So I have 3. So this is my fuel type diesel. Fuel type. Oh God. Let me make it bigger. So I have 3 different values, right? So it can be CNG, or it can be diesel, or it can be regular gas, okay? And I have 2 different dummy variables, right? K minus 1. three different values, three different categories, minus 1, that's 2, right? That means that my first one is fuel underscore type diesel, and another one, another dummy variable, fuel type gas, right? So if the car runs on diesel, so in other words, I have this case, right? What do you think the value fuel type diesel should be? 0 or 1? In our case, remember we discussed that 0 means no, 1 means yes, right? That's standard way how to encode yes, no. So if car runs really on diesel, the value for fuel type diesel variable should be 1, and the value for fuel type gas should be 0, right? So the car runs on diesel, not on gas. That's what literally it means, right? Okay, cool. Oops, I erased this one. If the car runs on gas, the value for fuel type diesel variable should be 0, and the value for fuel type gas variable should be 1. If the car runs on CNG, does it run on diesel? No, so this one is 0. Does it run on the gas? No, this one is 0, right? And that's essentially how you can differently interpret or record the same exact equation, okay? So let me go back to my equation here, okay? So instead of having this type of record, 0 if metallic, plus 42 if non-metallic, here's what I can do, okay? So instead of this record right here, I'm going to say plus the value 42.663 times the variable metallic, okay? Instead of this one right here. So I can erase that, and that's essentially how I can add this variable to the model, okay? So if the color is metallic, then metallic equals to 1, and therefore I have plus 42.63 to the equation, right? But if the color is non-metallic, then the variable metallic is equal to 0, therefore 42.63 times 0, nothing, right? It's the same thing, essentially, okay? Very similarly over here, I can go ahead and say, oops, I erased the number, hold on, undo. So here I can go ahead and say plus this value times the variable automatic, okay? And exactly the same thing happens, okay? If the car is automatic, then the variable automatic equals to 1, and I have plus 186.22. But if the car is manual, then automatic equals 0, and nothing plus 0 is getting added to the equation, right? And same exact thing here, okay? So instead of this three terms, I can go ahead and say plus 774.27 times fuel underscore type diesel, okay, and plus 1116.2 times fuel type gas, okay? So if the car is running on diesel, then this variable, fuel type diesel, equals to 1. So I have plus 774, right? The fuel type gas equals to 0, so that term is gone, right? The car runs on the gas, then fuel type diesel equals to 0, that term is gone. Fuel type gas equals to 1, and I have plus 1116.2. But if the car runs on CNG, then diesel, this dummy variable is 0, this dummy variable is 0, and therefore nothing, right, is getting added to the equation, okay? So in other words, I can formally use this output to write the equation just like that, okay? Bearing in mind that the dummy variables that I have, how many of them do I have? From the fuel type, I have 2 dummy variables, right? From metallic, I have only 1, right? Because there are 2 values, metallic 0 and 1. There are 2 of them, minus 1 is 1. All that I need is 1 dummy variable, right? Same happens with the variable with automatic, okay? It's 0 and 1. So there are 2 levels, minus 1 is 1. All I need really is 1 dummy variable, okay? So that's the idea, basically, how I can include categorical predictors in my equation. Make sense? kind of, sort of, I can formally write it out just like what I did before, right? The coefficient from the equation times the variable. Another coefficient from the equation times the variable, okay? The difference is that if the variable is predictor is numerical, then I have my good old interpretation, right? What's the, talking about interpretation, right? How do I interpret, for example, I don't know, age, for example, this one. Remember? We discussed interpretation of coefficient. How do I interpret that number, negative 133.04 times age? The slope is negative 113.04. How do I interpret that in plain English language? Yeah, exactly, right? So if age goes up by 1, and in this case, I believe in the file, ages are months. So if the car gets older by 1 month, then its value changes by this much. Okay? In this case, it goes down because of the negative sign by $133.04. Okay? So for each month, so if you keep a car for 10 months, right, without ever driving it or doing anything else, okay, the value will go down by the slope times 10, right? So it's essentially $1,330. Okay, so that's how we interpreted the slopes for the numerical predictors. But since we recorded the categorical predictors pretty much in the same way, right? Interpretation is similar, but not quite, because now we have to compare that value of the category, for my predictor, against the base one, right? And the base is everything is 0, right? So this one, automatic car, is worth $186.22 more compared to the base, which is manual. And we have to add every time, provided that everything else is the same, right? It has the same age, it has the same mileage, number of doors, weight, etc., right? Fuel type. The only difference between two cars is one is mechanical transmission, another is automatic transmission. Okay, so the meaning of these slopes is we compare that by how much the value of the car in this case changes compared to the base case or to the benchmark category. Okay, and that's all. All right. Any questions about how do we write out the regression equation and how do we interpret the coefficients for the regression equation? All right. Now let's discuss overfitting. You see, we keep coming back to the same idea again and again and again. Let me tell you one amazing fact. Okay, the more variables I throw into the model, the better R squared becomes. Always. Okay, this is amazing and to a certain degree unfortunate fact. Okay, for example. How many of you are finance majors? Let's see. Cool. So you know that stocks are going up and down every day, right? And there are a lot of people who try to make living out of it, trying to predict which way the stock will go and which stock will go up or down today, right? Let's say I'm looking at the stock of company Microsoft. Okay, great company. Stock was going up all, last few months. What do you think affects the value, how much Microsoft stock will cost tomorrow, a week from today, a month from today? What can be some of the things that are affecting the price of Microsoft stock? Public perception, yeah, if they screw up too much, their stock is going to go down, right? Earnings, right? How much money they generate. Dividends effect, right? So they start paying higher dividends, investors will see more value, and they'll start buying the stock price will go up, right? So there are some objective things that we can relate, like, for example, interest rates in the economy, right? So what happens when the interest rates are increased by the Federal Reserve Bank? Well, then investors start rebalancing their portfolios, right? So if the Federal Reserve rate is higher, that means that the federal debt getting higher rates, right? So investors start buying more U.S. treasuries, right? And where do they take the money? out of stocks. They start selling stocks, buy treasury. Stocks will start going down, right? So there is this effect as well. Let me ask you this question. What if I try to build a regression model that predicts the price of Microsoft tomorrow, and one of my predictors would be daily temperature in the city of Newport News? Will that be a good predictor? From general standpoint, it's going to be a bad one, right? I mean, what temperature here in Virginia has anything to do with Microsoft's stock price? Apparently nothing, right? But here is the amazing fact. If I start throwing random garbage like this one into the model, you will see R squared climbing up, always, okay? So every time when I add another predictor to the model, and it doesn't matter if this is a good predictor or bad predictor, the R squared will always go up, because there are accidental called spurious correlations, okay? It's just basically on some days, yeah, temperature here goes up, Microsoft stock goes up. That happens sometimes, okay? There's an accidental correlation. And that will basically bump up my R squared. So therefore, if I'm a statistician, here's what I'm inclined to do. If I want to build, and we discussed that R squared is one of the main things that how we evaluate how good or bad is the model, right? So from my standpoint, if I want to build excellent model with huge R squared, what I need to do? I need to throw in as many variables as possible, okay? I don't care really if they're good or not. If I put in 10,000 predictors, my R squared will be really high. But guess what? Most of that is going to be garbage predictors, right? They're going to be like temperature in the city of Newport News. That has nothing to do with Microsoft stock price at New York Stock Exchange, right? So therefore, here's what we're going to do, okay? From now on, let's do this. We're going to evaluate how good the performance of the model, not based on R squared, multiple R squared, but based on another measure. It's called adjusted R squared, okay? So here's what statisticians came up with. They said, okay, we understand that there is a desire to put as many predictors into the model just to artificially inflate, make it bigger, the R squared, right? So therefore, let's do this. Let's calculate something that's called adjusted R squared. And here is the formula, okay, if I remember it correctly. 1 minus n minus 1 divided by n minus k minus 1 times 1 minus your multiple, your regular R squared, okay? Here's what happens, ladies and gentlemen, okay? Oh, and here is number of records in your data set, okay? So sample size, let me call it, sample size, okay? Number of records in your data set, records. And K is number of predictors. Okay? So here's what happens, ladies and gentlemen. Suppose I want to add one more variable to my model, whatever it is, okay? So from K, I want to go to K plus 1, right? I want to add another predictor variable, okay? Now, what happens if my predictor is not very good? It does not add much value to the model. Well, my R squared, multiple R squared change a lot. The variable is predictor is bad. Will that affect the accuracy of the model, with or without the variable? What do you think? If I'm adding the variable, that has nothing to do with what I'm modeling. Like for example, in this case, it's hard to come up with, right? So, price of the car. Let's say I want to predict the price of the car based on the age of the owner or something like that. It's a clunky example. That has nothing to do with price, right? How old is the owner of the car? Who cares, right? So if I add this variable to the model, will my R squared jump by a lot? Probably not, right? So therefore, if I'm adding useless variable, this is what's going to happen. Multiple R squared is going to be the same pretty much, more or less, okay? But since my K is getting higher, right, I just added one more variable, then my denominator is getting smaller, right? So if I'm dividing by a smaller number, I'm getting what? A higher number, right? So therefore, from 1, I'm subtracting a higher number. What happens to adjusted R squared? It starts going down, right? So this is exactly what adjusted R squared does, okay? That's the purpose why it was designed and introduced by statisticians. R squared, adjusted R squared, will start going up if you add a good, significant variable. If you add a garbage variable, adjusted R squared will start going down. It will punish you, okay? So this is basically a way to control amount of useless or garbage variables. Okay, so let me actually draw you a picture. So this is what the picture will look like. Okay, so this is number of variables, k, number of variables, predictors, number of predictors. Okay, all right. So I told you that if I start adding to any model more and more and more predictors, what will happen to the regular multiple R squared? It will start go up, okay? So it will start looking like this. It goes up and then it kind of flattens out because, you know, you add real trashy variables, real garbage that has nothing to do with what you're trying to model. It will still go up, but by very little, okay? So therefore you will see diminishing rate of returns, if you know what I mean, right? Every next variable will have a teeny tiny effect on your R squared. But it will still go up, okay? It will never start going down. But, and this is your regular, okay? Multiple R squared. Multiple R squared. This is how it behaves. The more you add, the more variables you throw into the model, the higher it goes, okay? Even if by teeny tiny amount, it still goes up, never goes down, okay? But your adjusted R squared will behave like this. Your adjusted will keep going up until a certain point, okay? And this is basically where you will exhaust all of your good variables, okay? After that, you're starting to throw garbage to the model, right? Things like temperature in the Newport News, right? That has nothing to do with price of Microsoft, okay? And adjusted R squared will start from that point going down, okay? So this is how adjusted R squared behaves. Adjusted R squared, okay? It keeps climbing as if you keep adding really valuable, significant predictors, okay? But once you start adding things that are not really contributing anything to the model, adjusted R squared will start falling down, okay? So from that standpoint, this is your optimal model size, right? This is your golden K, number of variables, right? So from that standpoint, here's what happens. If I'm in area A, let me call it area B, A and B, okay? In area A, I keep adding valuable predictors, agree? I add one more variable, my multiple R squared goes up, my adjusted R squared goes up, okay? So if I'm in area A, I'm underfitting the data, okay? In other words, there is a room for improvement, and I can make good improvements by adding good predictors, right? Both adjusted and R squared, they go up, okay? But once I pass this K star point, then basically adjusted R squared says, well, this is it, man, you're tripping, okay? You're adding stuff just for the heck of adding stuff, okay? It's not really raising your R squared, so therefore I'm going to start punishing you. So adjusted R squared goes down. So in this area, in the area B, I'm doing what? I'm overfitting, really, okay? It's too much, right? I'm trying to artificially inflate my model accuracy by throwing garbage at the model, okay? I shouldn't be doing that. So this is overfitting area, essentially. And this is the optimal, apparently, model size, okay? Another important aspect of developing the model is model should not be overly complex, okay? So a lot of predictors does not necessarily mean a good thing. A model should be interpretable and it should make sense. Okay, so if I find that Microsoft price depends on the temperature in the city of Newport News, that will raise questions, right? How did you come up with that? And how do you explain that? It doesn't make much sense, right? So therefore, if model becomes too complicated or just plain stop making sense, then there are legitimate questions. Are you really doing the right thing or not? Okay? Well, then the question becomes, how do we judge which variables are good and they should be left in the model versus which variables are bad and therefore they should be extracted from the model? Well, ladies and gentlemen, remember what we did 2 classes ago. How did we judge if mileage was a significant predictor? We tested the hypothesis, right? Here's what we tested. What was my null hypothesis? Null was that the slope, and the slope in the United States is m, right? Letter m. So if I have slope for the variable number I, whatever it is, and I can set it equal to 0, that means that variable I is what? Significant or not? Not significant, right? Variable I, I'm going to quote unquote I, is not statistically significant. Statistically significant, right? In other words, I can replace it significant. I can replace it with 0, the slope for this variable. And therefore, after that, whatever value this variable takes, get multiplied by 0, the effect is 0, variable doesn't affect anything in my target, right? Doesn't matter, doesn't change anything really. And the alternative was that the variable I has the slope which is not equal, cannot be set to 0, well, which means that the variable is important and it has to stay. How did we decide to keep null or reject the null? What are we looking at? Start with p. P-value, right? And we said if p-value is less than significance level, then what do? Keep the null or reject the null? Reject, right? Always. All hypotheses in statistics are specifically, that's by design, they're formulated in the way that each time when you calculate p-value, you compare it against alpha, and if it's less than alpha, which you picked, right, and you reject the null in favor of alternatives. This is a universal rule for all possible tests in statistics, okay? Now, the only thing that I have to choose is alpha, right? What do I consider to be significance, right? So, what's the standard value of alpha? Oops. Wow, look at that. What's the standard value of alpha? 0.05, right? 0.05. This is standard value. Standard. That's called significance level, right? Let me write that down. Standard level of significance. All right? Alpha equals 0.05. Well, let's adopt this approach, okay? Which basically means that if my p-value is higher than 0.05, right? Come on. Don't be stubborn. Okay. If my value is greater than 0.05, what do? I keep the null, right? I don't reject it. And if I keep the null, that means that I can replace the variable with 0, slope, right? For the variable with 0. And after that, the variable is pretty much useless, right? I can get rid of that in the equation, and the equation will not get much damage, right? So let's do this, ladies and gentlemen. Let's go back to our output and let's see. All right, here is a bunch of variables, right, corresponding to the predictors, a bunch of slopes corresponding to the predictors, which I have, which I have in my model. Okay. Here in the last column, remember we discussed that. In the last column, I have p-values, right? Probability greater than absolute value of t. Okay. Do you see any candidates for natural deselection, so to speak? How do we decide? If p-value is greater than alpha, let's pick alpha 0.05 standard. Okay. Do we see anything that maybe is useless? Say meow. All right. Now tell me, do you see any variables which are candidates to be removed from the model? Which metallic? Yes, metallic. 0.65. What else? Engine volume, right? That's the highest one, really. Number of doors, 0.29, right? Automatic, right? Well, I have also diesel, 0.07, but unfortunately, diesel is a package deal, right? I can't just remove diesel and keep gasoline, right? It's kind of different dummy variables which were sort of created by the fuel type, right? So I can't remove one of them and keep the rest of them, right? So it's kind of all or nothing type of deal. Okay. Well, let me ask you this question. If I would have to remove a variable, which one should I remove first? What do you think? Engine volume. Why? It has the highest p-value, right? And that's exactly what we're going to do. So if you approach it like this, this procedure is called elimination. Okay, so I believe it's called stepwise elimination, right? So essentially you're looking at the model and you're picking the most useless variable. How do we pick the most useless variable? It has the highest p-value, right? If the p-value is highest, that means that this one probably, out of all variables, this is the least important, right? So therefore, we're going to have to remove them one by one, okay? That's an important thing. That's why the procedure is called stepwise elimination. Here is the reason. Each time when you remove something from the model, you have to recalculate the model, and it can happen that some variables, which are insignificant, when you remove something, they will become significant, okay? Because everything will get recalculated. You will get different slopes, you will get different p-values, so don't just remove, like, right now I see 4 of them, and I won't remove all 4. No, I have to do it step by step, okay, one by one. Stepwise, backwards elimination. So the idea is I kind of throw all of them against the wall, right? I got all predictors that I have into the model, and then I'm going to start removing them one by one. And when do I stop? When all the remaining variables are non-removable, right? They're all significant, okay? That's essentially the procedure. So, now, again, let me ask you this question. True or false? If I remove, what's the most useless? Engine volume, right? What do I expect to happen with my adjusted R squared and multiple R squared? Adjusted R squared will go up or down? It'll go up slightly, right? It will reward me for removing junk variable, right? Remember that? If you add useless variable, it goes down. If you remove, it goes up, right? My adjusted R squared, I'm expecting to go up. Maybe not by a huge amount, but go up. What will happen to my normal, regular, multiple R squared? It will go down, right? Because every time you remove anything, junk or regular variable, it goes down, right? Well, let's see. Oh, you tell me, how do I remove the variable engine volume from the model? Minus, right? Dot, everything minus engine underscore volume. And I'm going to rerun this thing, right? Is that how it's spelled? Engine volume, yes. Okay, so, oh yeah. What are my R squared? My multiple R squared, 0.8614. Not bad, by the way, right? Forgot to mention that. Our previous one with mileage alone was 0.35. Now I get it to up to 0.86. Not a bad increase, right? You see that I add more dimensions of the reality to the model becomes better. Not a big surprise, right? But now I have to eliminate things that do not seem to be important, right? So 0.8614 is my multiple R squared, and adjusted is 0.86. Okay, so I'm going to rerun this model and look at the summary. Multiple R squared did not move by much, right? Stayed pretty much the same, 0.8614. What happened to adjusted R squared? It went up by teeny tiny amount, right? You see that? I removed the thing that was not making a big contribution, right? Volume, engine volume. And adjusted R squared said, yeah, I like that, okay? I'm going to reward you with higher value, okay? You're doing good so far. All right. What's the next candidate for this selection? Metallic color, right? Seems that metallic versus non-metallic doesn't really make much contribution. So I'm going to remove metallic. I'm going to rerun the model and look at the summary again. Now look at that. My adjusted R squared said, yeah, I like that. 0.8602. Now improvements are, of course, teeny tiny microscopic, right? But at least it's kind of an indication that at least I'm doing the right thing, moving in the right direction. And by the way, adjusted multiple R squared went down a little bit, right? It used to be 0.8614, now it's 0.8613. So R squared says, yeah, I don't like it. You're removing variables. But my adjusted R squared says, no, it's actually a good thing. You're removing junk variables, right? They were not making a lot of contribution to begin with. Make sense? All right. So what's the next one? Oops. Automatic, right? 0.39. So let's subtract automatic minus automatic. All right. Let's rerun the model. Let's see. Oh yeah, adjusted R-squared keeps climbing, right? 0.8603, and multiple R-squared keeps going down. Now, small changes, but they basically tell me that I'm actually removing useless stuff, right? And one last thing that apparently is not significant is this one, number of doors, right? So let's eliminate number of doors. So I'm gonna do that, minus number of doors. Boom. Okay, so adjusted R-squared doesn't really change much, right? And multiple R-squared didn't really change much, if I remember. Yeah, it goes down. Yeah, so it looks like I'm kind of, no, actually adjusted R-squared did go up a little bit, right? Yeah, did go up a little bit. All right, so, oh, hold on. Did I remove number of doors? No, why not? Real estate. What real estate? Hold on. Number of doors. Let me run it again, and let's do the summary. Okay, now I removed it, okay? So now my adjusted R-squared starts going down, right? It basically tells me that, yeah, you reached the peak, right, and now you're on the downward slope, right? And that's what my p-value is also telling me, right? If I'm looking at the p-values, but with the exception of fuel type diesel, everything else seems to be relevant and significant, right? So this is my pretty much optimal model right now, okay? It's not overfitting anymore, and it's not underfitting, well, at least within these variables, right? I don't know. Maybe I'm missing something, right? You don't know what you don't know, basically, okay? So can this model be improved? Well, probably, right? The model does not have number of owners, which may be also an important thing, right? Number of accidents as reported by Carfax, right? So extra features that may increase the value of the car, also not part of this model, right? So I may have a better model, but I just don't have this data, right? So with the data that I was given, this is the best I can get. At least I think so, okay? Now let's see what happens if I remove one of the important variables. What do you think will happen? It will all start going down, and quickly, right? For example, let's do the first one on the list, age, right? What if I will rerun my model without age? So subtract age of the car, and let's run this thing, and let's do the summary. My multiple R-squared 0.69. Do you see the huge drop? That's how you know that the variable that you removed is actually significant, okay? The ones that you did before, you remove them, your multiple R-squared start dropping, but it drops by like 1,000 or 10,000, right? And now I remove the variable that was really important, and my R-squared says, okay, now I'm dropping like 15 points, 15% down, okay? That's how you know that the variable was important. You get immediate hit on R-squared and adjusted R-squared as well, okay? You can see that both of them went down quite a bit, okay? Make sense? So this is the backwards, stepwise linear regression process, ladies and gentlemen. So I'm going to put age back into the pool and rerun it, and this is the best that I can do, okay? So right now, my R-squared is not bad, 0.86, adjusted 0.86, okay? So given the variables that I had, given the data, that's probably as best as I can do, okay? Which is not bad at all. Any questions, my quiet friends? All right, how much time do we have today? All right. Looks like natural stopping point for today, right? So on Wednesday, we're going to take a look at another very important consideration, and that would be, we didn't look at the residuals yet, right? So we're going to calculate residuals. And we're going to take a look at another very important consideration for multiple regression. It's called multi-collinearity. Sometimes, when your variables are strongly correlated predictors, you get some weird results, okay? So that's what we're going to do on Wednesday. All right.